Assalamualaikum and a very good afternoon. Today we are going to step in the last chapter of the course entitled the filter design. So you are going to apply the knowledge that you have learned in chapter 5, which are the transfer function, dot plot, and filter response or frequency response in this chapter. So from the figure you can see lots of lines which represent filter response of different types of filters. So there are many types of filters such as listed underneath the figure. So you can see that there's filter with ripples on top. Okay, so this basically represents the low pass filter. Okay, you can see that the bigger area for passband, and on the right hand side is the stop band. So you can see that different types of filter will be having a different response in the passband and in the stop band. To discuss two types of filters, which are the Chebyshev and Butterworth. Okay, so Butterworth and Chebyshev filter will be having different types of response. For example, in the transfer function itself. So the first one shown is the transfer function for Butterworth filter. You can see that constant 1 on top. Okay, constant 1 on top, and then at the bottom there's s to the power of n. N is the filter order number that you need to determine before you can design a filter, and then series of a's. So a is basically the coefficients or polynomials of the filter. Okay, next is the transfer function for Chebyshev. So in comparison with Butterworth, okay, Butterworth having constant 1 on top. However, for Chebyshev you have the Kn. Okay, so Kn dependent on the filter order number, whether it is even or odd. If n is odd number, so the numerator will be a0. Okay, this is the coefficients that you'll be getting those the values from the table. And if n is even number, so the Kn represented by this equation. So all equations you can refer from the filter characteristic appendix or from the table. Okay, you don't have to memorize all the equations. Okay, let's look at the comparison between the Butterworth and Chebyshev. So the graph shown here is for Chebyshev. You can see that the frequency response of Chebyshev filter having ripples at the passband. Okay, it has the ripples at the passband, while it has fast roll off. Okay, the slope goes down quite significantly before it reaches the stop band area. Okay, so the signal attenuates quite fast. Okay, if compared to Butterworth filter, it has flat top in passband area. Okay, it is flat top. If compared to the Chebyshev, it has ripples, but for Butterworth, the passband area having a flat top signal. Okay, flat top, and then the roll off, the signal drops down a bit slower or in steady state if compared to Chebyshev filter. Okay, before it reached the stop band. Alright, so WP, omega P representing the passband frequency for C is for Chebyshev, while B is for Butterworth. Okay, so and then omega S is a stop band frequency for Chebyshev, and omega SB is the stop band frequency for Butterworth. Okay, if you look at the magnitude, maximum magnitude. Okay, so in this case it uses linear values, and normally we'll be using a dB values. Okay, so either it is in dB or in linear, but in this case it is in linear. Okay, so the maximum amplitude of the filter is 1, and then alpha P is the passband gain. Okay, in dB or in linear, but usually we will be using the dB values, and 0.707 is equal to minus 3 dB. Okay, this is where the cut-off frequency takes place. Okay, so 0.707 or minus 3 dB, where you can find the cut-off frequency. Okay, omega C. Same goes to the Butterworth filter at minus 3 dB. So you will be having your cut-off frequency. So this one is omega C for Butterworth, and the other one omega C for Chebyshev. Alright, and then at omega S, at the stop band frequency for both Butterworth and Chebyshev, that's a stop band gain. Okay, so given by alpha S. Right, so the main key point or the comparison between Chebyshev and Butterworth, in terms of first one, is the ripples. Okay, if you see there's ripples in the passband area, so it belongs to Chebyshev, while Butterworth, it is called flat top or no ripples at passband. Okay, and then fast roll off, meaning that the slope. Okay, look at the slope. For Chebyshev, it has fast, or the gradient is very the slope is very narrow if compared to the Butterworth. Okay, fast, steady and slow roll off. Okay, in terms of circuit generation, okay, Chebyshev much simpler, while the Butterworth having a bit complex circuit generation. And Chebyshev is also known as equal ripple because it has ripples in the passband area, while Butterworth is also known as maximally flat. Okay, let's look at the filter response for Chebyshev. So again, Chebyshev, it has ripples. So the ripples magnitude is given by A max, and usually it's given in dB values. Okay, and if this is the linear values, so you can compare with dB values axis. So if it is 1 in linear, so it's 0 dB, and then alpha p, you have the gain in negative x dB. Okay, for alpha p in the passband gain, and 0.707 is the cutoff area, so it's given by minus 3 dB. So it's minus 3 dB from the maximum, so the maximum power is 0 dB. Okay, and then alpha s, the stop band gained, you have, for example, negative y dB. Okay, so the stop band gained will be having the stop band frequency at omega s, and then the cutoff frequency omega c at minus 3 dB, and then you have omega p, the passband frequency in radian per second for the passband gain area. Okay, filter response for the Butterworth filter. Okay, so it's flat top, no ripples in the passband area. So we are using the low pass filter response in this case. If you have high pass filter, so it looks something like this. Okay, so still flat top samples, and then you have maximum gain of 1 or 0 dB, and then you have passband gain, and you have the omega p. So in high pass filter, so for high pass filter, so you have maximum here is 0 dB, and then you have passband gain alpha p, and you have the omega p. And then for high pass filter, the stop band gain omega s is the stop band frequency, and alpha s is the stop band gain. and then you have cutoff frequency of omega c at minus 3 dB. So here is omega c, and you have, we can call it alpha c or negative 3 dB. Okay, so for the cutoff area. While for the low pass filter, again here is minus 3 dB. So you have the omega c, and then alpha s, you have the omega s for low pass filter or for low frequency filter. But for high pass filter, you'll be having the passband area on the right hand side. Same goes to the Chebyshev just now. So if you have high pass filter, so the ripples will is occurring at the passband area on the higher frequency part. Okay, let's look at how to design a Chebyshev filter. Okay, so these are the processes involved in designing Chebyshev filter. So the first one, you need to determine the filter specification, type of response, whether it is low pass or high pass. Okay, so Chebyshev, obviously you know that the frequency response should be having ripples at the passband area for low pass filter, and for the high pass filter you'll be having ripples as well in the passband area. Okay, next you need to write down the transfer function. Okay, you'll be having two types of transfer function, which are the normalized transfer function given by H and S. So the equation will be provided in the appendix of filter characteristic, and another one is the actual or final transfer function given by HS. Okay, this is an example of normalized transfer function, and it depends on the filter order number. Okay, if you notice here you have n, so it depends on the filter order number, and at the bottom you have the a values. Okay, so a is called coefficients, or the denominator is called a polynomial. Okay, lastly you need to perform circuit realization. Okay, so the basic structure consists of the source, voltage source, and then you have the resistor, constant resistor, and then you have combinations of C and L. Okay, so the number of C and L combinations depends on the filter order number and also the max value, the ripple magnitude. Okay, these are the same steps as mentioned earlier. So the first step, you need to calculate the order number. Okay, in order to get the filter specification, you really need to calculate the n in the first place. Okay, so the filter order number, so either is n odd or n even. Okay, and then you need to refer to the appendix again for Hn equation, the normalized transfer function. And then, so in order to have normalized transfer function, you also need to refer to specific table to determine the polynomials or the coefficients values. So A1, A0, and so on. Okay, once you have the normalized transfer function, then you need to write down the actual or real transfer function. Okay, so in order to transform the normalized into actual transfer function, you need to refer to transformation table to get the transformation equation, and finally the circuit realization. Okay, the most important part in this chapter, you need to refer to lots of appendices. Okay, so and it depends on types of filter you'll be designing. Okay, for example, if you notice that the filter response having a ripple in the passband area, so you know it belongs to Chebyshev. Okay, so you need to refer all equations from Chebyshev. Okay, otherwise, if you have flat top samples, this is for example for high pass filter, flat top samples, so it belongs to Butterworth filter, so you need to make sure that you refer to all equations under Butterworth appendices. Okay, so in here we'll be seeing the AMX. AMX only appear in Chebyshev because it represents the magnitude of the ripples. Okay, so the epsilon. Okay, epsilon is the ripple factor. You can calculate by using this equation. Okay, so Mx is in dB. So you just put in the dB values, positive dB values, although the value is negative. Okay, same goes to the end, the number of filter order, and this is omega Sn, the frequency, normalized frequency, and omega Sn is not equal to omega S, so it's different. Okay, so it depends on types of filter you have, whether it's low pass or high pass. So you need to refer to a table to get the actual equation of omega Sn depending on types of filter you have. And alpha S, the stop band gain, and Mx is the magnitude of your ripple, so all in dB. Okay, if for example Mx is given as 1 dB, so you just put in 1 in here. You don't have to convert these dB values into linear. Same goes to the alpha S. If alpha S, for example, minus 30 dB, so you just put in 30 in here. You don't have to consider the negative, and also you don't have to convert into linear values. Okay, so please make sure you put all parameters in dB values. Right, and then omega C is the cut-off frequency, omega P is passband frequency, cos hyperbolic. Okay, please make sure you calculate properly using your calculator and make sure it is cos hyperbolic. And then this is inverse cos hyperbolic cos. Okay, again this is the epsilon is the ripple factor. And for Chebyshev, you have the Kn. It depends on the filter order number, whether it's odd or even. Okay, same goes to Butterworth. So in the first part, I'll be discussing on Chebyshev, and in the second part, I'll be discussing on Butterworth filter. And these two slides summarizes the formula that you will be using throughout the filter design. So you can refer to the appendices for more equations. Okay, after we have determined the normalized transfer function and the actual transfer function, the next step is to design the filter circuit for the respective filter. So depending on the question, whether the question asks you to design a filter circuit or just a transfer function. If the question didn't ask for filter circuit, so you can just stop until the actual transfer function. So in filter circuit realization, so you'll be seeing combinations of passive components, resistor, inductor, and capacitor. And as mentioned earlier, the total of C and L combination dependent on the filter order number and also the ripple magnitude. Okay, this is the basic representation of normalized filter circuit. So it consists of the voltage source and then the normalized resistor values. Okay, followed by combinations of C and L. You need to start with C, the capacitor, followed by the inductor, and then continue again with capacitor, inductor, and so on. Okay, so number of C and L combinations dependent on your N, the filter order number, and also the max values. Okay, so the circuit need to be terminated by a load represented by the RL. Okay, so in final Chebyshev circuit, you'll be having the same configuration, but all R, C, and L values will be converted into new values, and there's formula to calculate the new R, C and L values. Okay, as mentioned earlier, this is the general sequence of the filter circuit. So you need to refer to table F.2a or F.2b. Okay, these two tables basically for different Mx value. For F.2a representing the circuit for Mx equal to 0.1 dB, while the F.2b represents the circuit values for Mx equal to 1 dB. So you need to refer to the correct table. Okay, this is for example, you have Mx equal to 0.1 dB and N equal to 3. So please look at the table properly. So for Mx equal to 0.1 dB and for N equal to 3, so you'll see that you have C1, L2 and C3. Okay, so you need to draw the circuit. So you have your Vs here, and then you have the normalized resistor given by Rs, and then you have the first one must be C, so it is C1, okay, followed by L2, and you have last one is C3. Okay, that's all the components you have, and the circuit must be terminated by RL. Okay, once you have all the parameters in, don't forget to put in all the values in your circuit as well. So Vs depending on the voltage source given to you. So Rs, if it is not given, you can assume Rs equal to 1 ohm. So C1 in this case is 1.0316. The unit is F, and L2 is 1.1474 Henry, and C3 is 1.0316. All right. So RL dependent on the load given to you. Okay, let's look at an example on Chebyshev filter design. So design a Chebyshev low pass filter. Okay, the first keyword is low pass filter with the following specification. So I recommend you to draw the filter response so that you can see where the alpha P, alpha S, omega P and omega S location or values. So this one in dB. So it's Chebyshev low pass. Okay, so low pass filter. So the signal will be having ripples in the passband area. Okay, and then roll off. Right, so the Mx is 1 dB. So this is your Mx. Okay, Mx for, so here is 0 and here is 1. And then from omega is from 0 until 10. So your omega P equal to 10 radian per second. And your alpha P is minus 1. So the passband area. Okay, followed by a stop band not to exceed these values. So alpha S is negative 30 dB, and for omega S equal to 20 radian per second. And then you have another one, the cutoff frequency. This is negative 3 dB, and you have your omega C there, so which is not given. So given RL equal to 100 ohm, so you need to find the HS, meaning that you need to get the actual transfer function, meaning, and you need to know the H and S first before you can get the actual transfer function. Draw the circuit, meaning that you need to have the final circuit, so you need to have the normalized circuit first, and then convert it into the final circuit. Okay, so I would recommend you to draw the filter response. Okay, that's marked for steps. Okay, so the first step, you need to calculate the filter order number. So this is Chebyshev, so make sure you refer to the correct appendix for Chebyshev filter and write down the general equation first. Okay, do not put any value straight away. Write down the general equation first, then you put in the values in the second equation. Okay, so this is the filter response that we have drawn earlier. Right, so please remember you need to use dB values inside your equation. So alpha S equal to minus 30 dB, so ignore the negative, so just put in 30. Okay, and then Mx given as 1 dB, so just put 1, and cos hyperbolic, inverse cos hyperbolic, and then omega Sn you need to refer to a table. Okay, so which table it is? It is table F.1. Okay, and refer to specific type of filter. This is low pass filter, so omega Sn for low pass filter given by omega S over omega P. So in this case, your omega S is 20 and omega P is 10. So your omega Sn is 2. So then put in all values you have into the general equation. Okay, so omega Sn equal to 2, and then your alpha S minus 30 dB, you just put positive 30, you don't have to consider the negative, and then Mx equal to 1, so you just put 1. Okay, and then you have your N equal to 3.68. You need to round up your N values to the next higher whole number. Okay, even if you have N equal to 3.1, so still your N should be equal to 4. Okay, if N equal to, for example, 2.05, still you need to round it up to the next higher whole number, so N equal to 3. So keep that in mind. Okay, once you have the N values, so from the earlier calculation you get N equal to 4, so it is even number. So to write down the equation, the transfer function for Chebyshev filter, so N even number, so you need to calculate the Kn values. Okay, because Kn is on top, the numerator. So the Kn, you can either use this equation or this one. But in this case, since we have the Mx values, so you can simply use this equation to get the Kn values. So what is A0, A1, and so on? It is the coefficients. So next, you need to refer to table F.4. Okay, for coefficients. Okay, so in this case, the Mx is 1 dB, given as 1 dB. So make sure you refer to the correct one. Okay, it is coefficients for, please look at this column, this one for 0.5 and the second row for 1 dB. So make sure you refer to the correct lane. Okay, and in this case you have your N equal to 4. So please list down all coefficients values before you put in the values into your equation. Okay, because common mistake by students, they just put in the first value into the first position, second value into the second position, and so on. But if you look at the sequence, the first one is for A0, it's supposed to be at the back. That's why I would recommend you to write down your coefficients values first before you put in the values into the equation. So in this case, your Hn is equal to your Kn is 0.24. So you should calculate what is your Kn values. In this case, your A0 equal to 0.2756. So 0.2756 divided by 10 to the power of your mx is 1/20. You should get 0.24. Okay, so 0.24 divided by s to the power of n. So s to the power of your highest n is 4. S to the power of 4 plus n minus 1. So your A3, in this case, your A3 s to the power of 3 plus A2 s to the power of 2 plus A1 s plus the last one is A0. Okay, now once you have the general equation, then you can put in all coefficients values into the equation. Okay, so put in the coefficients values. So here is 0.24 divided by s to the power of 4 plus your A3. So your A3 is 0.9528 s to the power of 3 plus ... Okay, just put in your A values in. So this is your normalized transfer function. Okay, once you have your normalized transfer function, then you need to write down the final transfer function. So depending on the question, whether the question only asks you to write the normalized transfer function only, or you need to come up with the until final transfer function. Okay, in case of the question asks you to write down the final or actual transfer function, so you need to proceed to step 3. Okay, so this is the normalized transfer function from earlier step. So to get the final transfer function, you need to refer to table F.5 to get the conversion values. Okay, so this is how part of the table F.5 looks like. So you need to refer to the correct type of filter. So in this case, we have low pass filter, and you need to refer to the transformation equation. So meaning that all s for this particular example, so all s must be replaced by s over omega p. What is omega p? Is passband frequency. Okay, so the left hand side for the Chebyshev, while the right hand side as stated is for Butterworth. So in this case, we use the Chebyshev. Okay, so this is for the Chebyshev transformation. Okay, so all s in your normalized transfer function need to be replaced by new equation s equal to s divided by omega p. Okay, so in this case, your omega p is 10, so you need to replace all s with s divided by 10. So this is your actual or final transfer function. Okay, next, if the question asks you to provide the normalized circuit, so you need to refer to table F.2b in this case for Mx equal to 1 dB. So again, it depends on your n values and also your Mx values. Okay, so this is how the table F.2b looks like. F.2a is basically for Mx equal to 0.1 dB. So in this case, your n equal to 4. So refer to n equal to 4. So see how many components you have in your circuit. So your source, and then you have up to L4. So C1, L2, C3, and L4. Don't forget to write down the values inside your circuit. So you have C1 equal to 4.5699, and then L2 0.5428, C3 6.3680, L4 0.3406, and RL as stated in the question equal to 100 ohm. So this is the normalized circuit. Okay, you need to represent the sequence, and then don't forget to put in the values in your drawing. Okay, lastly, the final step is to represent the final circuit using circuit transformation. So you'll be using the same sequence as the normalized circuit. Okay, however, you need to calculate the new values of your components. Okay, so in order to get the new values, you need to refer to table F.3 circuit transformation. So this is low pass filter. So we have the low pass filter as stated in the question. So your L new will be calculated by using this equation, RLP divided by omega C. So LP is your the values in the normalized circuit. Okay, same goes to C. The CP is the values in your normalized circuit. While the R here, so in normalized circuit you have RS, but in final circuit you have R, can be calculated by dividing RL divided by RP. So RP values you can get from the earlier table. Alright, so here you'll see that you need to divide your earlier component values with omega C, the cutoff frequency. So you can calculate the omega C by referring to the equation. So it's omega P cos hyperbolic, this equation, and you have ripple factor can be calculated by using this equation. So Mx given as 1 dB, so just put in 1. So you get the ripple factor equal to 0.51. So then you need to calculate your omega C, and omega C will be used in your L and C new calculation. Okay, so this is from the normalized circuit. So now you need to recalculate your new values of C and L. Okay, same orientation, same number of components. However, you just need to recalculate the new values for your capacitor and inductor. Okay, so this maintained as load. However, here is R equal to RL over RP. Okay, so in this case, your C1 now become C by having conversion of C1 divided by R omega C. So we have calculated omega C in the earlier slide. So this is basically your final circuit or actual circuit of the Chebyshev filter. Okay, let's look at the second example on Chebyshev filter design. So as mentioned earlier, once you have the parameters or specification, I'll recommend you to draw the filter response. So this is the next design is for high pass filter. So high pass filter, and the specification as listed. So you know it is Chebyshev, so it has ripples at the passband area. So this is high pass filter with ripples. Okay, so Mx values given as 1 dB again, so 1 dB. Okay, so here is your stop band area. So here -1 is here is your alpha P, the passband gain, and then you have your alpha S equal to -22, and here is your omega S from 0 to 15, while alpha P, you have your omega P equal to 20. Okay, and as usual you have your -3 dB representing the cutoff frequency. Okay, so this is the filter response of high pass filter Chebyshev, and then as usual you need to calculate the filter order number. So n, so omega Sn, you need to refer to the table. So for high pass filter, what's the equation for omega Sn? So alpha S given as So alpha S is negative 22. So you need to replace alpha S with 22 divided by 10 minus 1. Okay, and Mx given by 1 dB. Okay, so from F1 tab F.1, so omega Sn for high pass filter is omega P over omega S. So omega P is 20 in this case, divided by omega S is 15. Okay, so replace omega Sn with this value, and then so make sure you do it properly. So 1 over inverse cos. Okay, write down the general equation first, then you put in the values in. Okay, omega P is 20 divided by 15, and then inverse cos parabolic. Okay, 10 to the power of alpha S. So alpha S is negative 22, so 22 divided by 10 minus 1 divided by 10 to the power of mx minus 1. Don't forget the square root here, 1 over 2. Okay, you should get your n equal to 4.9. So round it up to the next higher whole number. So n in this case equal to 5. Okay, once you have the n values, so you can write down the transfer function. So for high pass filter, Chebyshev, so n is odd. So when n is odd, kn equal to a naught. So where to get the n naught values, you need to refer to table f.4. So, and don't forget to refer to the correct AMX values. So in this case, your n equal to 5. So list down, please list down all n values, all a values before you put in the values into your equation. So this is the normalized transfer function. So your normalized transfer function equal to a naught divided by s to the power of 5 in this case, plus a4 s4 plus a3 s3 plus a2 s2 plus a1 s plus a naught. Okay, so write down the general equation before you get your final normalized transfer function. Okay, once you have your normalized transfer function, you can get the final transfer function by having some conversion or transformation. So please refer to table f.5. Okay, so this is table f.5, and in this case we have high pass filter, so make sure you refer to high pass filter equation for Chebyshev in this case. So S will be replaced by omega P divided by S. So your omega P equal to 20 in this case, so 20 divided by S. So from the normalized transfer function, all S must be converted into omega P over S. Okay, so then you can just leave your answer as this. Okay, you don't have to calculate the final equation to save time. Okay, next, if the question asks you for normalized circuit, so again you need to remember your n equal to 5 in this case, so mx equal to 1 dB. So refer to table f.2 b for mx equal to 1 dB, so n equal to 5. Then you need to draw the general circuit sequence depending on how many components you have. So you have your RS, we assume it is 1 ohm, and then followed by your C1, and then you have L2, and then you have C3 and L4 and C5. Okay, so you have C3, you have L4, and you have C5. Don't forget to terminate your circuit with RL. Okay, finally you need to put in all values in. So this is VI or VS, the source. C1 equal to 2.1349 F, L2 1.0911 H, C3 3.009 F, L4 10911 H, so C5 21349 F. And please refer to the question again, what is the RL value? So you need to put the values in ohm. So this is your normalized circuit. Okay, if the question asks you for final circuit, then you need to do circuit transformation by referring to table F.3 and perform the transformation as shown in the earlier example. Okay, lastly for today's session, let's have another example on Chebyshev filter design. So please try this out to familiarize yourself with the appendices and tables. Okay, this chapter will be asked in your final exam and it is compulsory for you to answer. So therefore you need to really focus on the steps, familiarize yourself with the table, make sure you can write down, derive the equation and put in the correct values depending on the specific type of filters. Okay, with that I end the session today. Thank you.